Okay, welcome to another video of Chem with Com. So we'll continue this lecture about molecular structure and polarity. Specifically, this one is going to be the third part. This is molecular polarity. So we on the last lecture, we figured out what polar bonds were, right? It's when one atom, or in a bond, one atom is more electronegative than the other. Remember, we're using up and to the right of the periodic table as the most electronegative. So this is going to be the most electronegative, which is partially negative. So this will be partially positive. Because one's partially positive, one's partially negative, it has what's called a polar bond, right? And that bond, this is the positive side, and this is the arrow points toward the more electronegative atom. And if you look at it this way, right, this is going to be partially positive, this is partially negative, and then, yeah, we have a dipole moment or a polarity vector, whatever you want to call it, and that tells you it's more polar. Sorry, not more polar, it's polar, it's a polar bond, and the electrons are pointing, the arrow's pointing toward the area with more electron density. All right, but let's take a look at the sizes of these vectors, right? They drew this one some length, but they drew this one shorter. The shorter vector means it's going to be less polar than the, less polar than the longer vector. So longer equals more polar, and then shorter means less polar. All right. Again, so we have are these polar molecules, right? We have polar bonds, but are these entire molecules polar, right? I talked about this briefly in the last lecture, but the Earth is polar because it has a north side and a south side, right? There's no like kind of north over here, right? It's all one side is north, one side is south. So if we split the Earth down the middle, right? North side and south side. That's the same difference between a polar molecule, right? We want to see that there's more electron density on one side of the atom versus the other. And so if you look here, let's assign partial negatives, partial positives, right? If we look at the electronegativity difference between carbon and oxygen, oxygen is going to be more electronegative. Carbon is going to be more electropositive. You look over here, right? The side's electronegative, right? Here, there is not one side that's positive, one side that's negative. So this would be non-polar. Another way to look at it is these vectors, these polarity vectors, right? We see that this arrow is exactly opposite of this arrow. Should be the same size, same length. So when they cancel each other out, right, there's no overall polarity. There's not one side of the molecule that's negative and one side of the molecule that's positive. So that's non-polar. All right, now let's look at water. Oxygen here, let's just do blue just for fun. This is going to be partially negative because oxygen is more electronegative than hydrogen. This is going to be partially positive. That's how we have that positive here, right? Partially negative, right? So the arrows are going to be pointed toward the oxygen. They're the same size. Now let's analyze this, right? We have an arrow going this way, and I'll try to draw it the same size. I probably can't do it exactly, right? They don't cancel each other out. Let's take a look here. Now let's draw these other. So we have one portion of the vector going this way and one going up. Here we have this way and up. Okay, now these two cancel each other out because they're opposing arrows, right? Cancel out. These arrows do not cancel. Do not cancel. So since they're both up arrows, the net dipole moment is going to be like this. It's going to be up. And let's draw this kind of the way they have it so it looks the same. But we have a hydrogen connected to an oxygen. And the overall dipole moment is just going to be straight up. Right? So that is a polar molecule. Right? Again, we have polar bonds and then we have polar molecules. They're different. Now we're talking about polar molecules. If you're looking for polar bonds, go back one lecture or one video and you'll see it. Okay, so let's look at this one. We looked at CO2, right? This is carbon dioxide, and this is OCS, right? All right, so here, what we're going to do is the arrows cancel out. It's not or non-polar because arrows cancel out. So the polarity vectors cancel out. Cancel. Okay, now let's look over here. Here, the oxygen and carbon, just like this one, have some sort of polarity, right? So we're going to draw the polarity vector or the dipole moment, whatever you want to call it. Or sorry, that's the polarity vector. The dipole moment's the total overall thing, right? But if you look here, so the electronegativity difference between C and O, carbon is 2.5, oxygen is 3.5, so that's 1.0. So we have another one here, CS. Let's do it over here. C bonded to S. Here it's 2.5 and 2.5. So it's effectively zero. It's going to be a small one because those numbers are rounded, but let's say we don't know that, right? Well, we know that this side is going to be now a little positive. This side is going to be, oh, sorry there, my bad. Over here is going to be a little negative, and this is going to be a little positive. Here, there's no polarity vector, right? Because there's no real polarity difference. But as you can see, this is going to be smaller. It can be zero or small. You're still going to have what's called the overall dipole moment, where one side of the molecule is negative, one side of the molecule is positive. And it's written there for you, but I'll just draw it again, right? Just so, because we know this side is positive, right? So even though this is the same shape, they're both linear, they both have carbon and oxygen in it. The only difference is this last sulfur. So it is polar. Polar molecule. It is a polar molecule. All right, so just by the arrangement of atoms, it's going to tell us if it'll dictate whether it's polar or not. Okay, so the book version is contain at least one polar covalent bond, have a molecular structure such that the sum of the vectors in each bond dipole moment does not cancel. That works most of the time, but my way works most of the time also. It's a little easier. So you're going to draw the 3D structure of the molecule. Most of the time, the Lewis structure just works. You don't have to do 3D. And then next, you want to label all the exterior atoms with their electronegativities. Delta negative, delta positive. And based on periodic trends, right? That's how you want to label it. Up and to the right is going to be the most electronegative. Bottom left is the least electronegative. And all you're going to do is draw a straight line that separates the delta positive atoms. Atoms, right? Not the actual charges, but the atoms themselves. If you can draw a line that separates positive side from negative side, it's polar. If you cannot, then it is non-polar. All right, let's look at these here. Okay, so here, fluorine, the most electronegative thing on the periodic table, negative. Hydrogen, carbon, these are going to be slightly positive. All right, can I draw a line that separates one atom that's negative from the rest? Yep. This side is partially negative, this side is partially positive, so this is polar. And this is CH3F. Okay, let's look at this one here. Hydrogen, this is all going to be partial positives. So can't draw a line that separates from partially positive side. So this is non-polar. Same thing here, partially negative, partially negative, partially negative, same thing. Non-polar, right? Because you cannot draw a line that separates the negative side from the positive side. All right. Okay, let's do some practice problems. All right, so basically we're going to draw 3D structures for all of them, label the positive and negative side. If they are polar, if we're going to try and draw a line, and if we can, that separates the positive side from the negative side, we're going to draw the dipole moment. And again, don't use the periodic table for the electronegativity values. Use the trends of atoms that are higher and to the right are more electronegative. So let's try this. Okay, H2, it's just H and H. We know they're the same electronegativity, so not polar. Cl and Cl, right? It's not polar because they're the same atom. They don't have, one chlorine's not stronger than the other chlorine. HCl. We know that H is going to be slightly positive, chlorine is going to be slightly negative. So we can draw a line through it that separates the partial positive from the partial negative. So this is our dipole moment. CO. We know oxygen's more electronegative than carbon because we can draw a line. Oops, let me just clean that up a bit. We could draw one line that separates the positive and negative ones. It's going to be this way. CO2, right? Oxygen is kind of slightly negative, so you cannot draw a line, not polar. All right, let's check this one out. This one's going to be a little fun. This is going to be carbon in the middle, bonded to hydrogens. This is double bonded to oxygen. Oxygen and carbon, partially negative. These hydrogens, partially positive. Well, we can draw a line right there. Partially negative, partially positive. This is polar, right? So again, if you can draw a line that separates the positive atoms from the negative atoms, it's polar. Just a one straight line. Don't get all fancy with curved lines and stuff. All right, CCl4. Again, if you need a review on Lewis structures and 3D structures, go back a few lectures and you'll catch those. But this is how to draw the 3D structure of CCl4. All right. Chlorine's more to the right, so it's going to be partially negative, partially negative, partially negative, partially negative. There's no way to draw a line. Now let's say, look here, carbon's here, chlorine's here. It's hard to follow the trend, right, of up and to the right, because carbon's up and to the left, chlorine's right and down, so it kind of opposing trends. But let's say all of those were positive. Is that going to change the answer? They're all positive? No, still not polar, right? So just make sure the details sometimes matter. This one it really doesn't, because regardless if the chlorine was positive or negative, the carbon's going to be the opposite. And no matter how you split that up, you will not be able to get that to be polar, right? All right, let's draw this one. Hydrogen, hydrogen. We got our little dash here, means coming out at us. Yep, can't. So partially positive, partially positive, partially positive, partially positive. Can't draw a line, so not polar. All right, C, H, 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 and F. Well, this is positive, this is positive, this is partially positive, this is partially negative, right? But if you look here, we can draw a line that separates the fluorine atoms from the rest of the atoms. And that's going to be the partially negative side. This is the partially positive side. So the overall dipole moment, maybe I forgot to draw those over there, but it's going to look something like this, going all toward fluorine. This one is polar also. The dipole moment is here. And then, all right. So now let's do H2O. All right, oxygen, we have, I draw it normally with the electrons on top. It doesn't really matter because it's all the same molecule. I just want you to be familiar with it. Hydrogen, hydrogen, that's the wedge coming out at us. And then the dashes, the dashed wedge is going to be the other set of electrons. Now, this is going to be partially negative. These are partial. The electrons have nothing to do with polarity, right? Even though they're negatively charged, they do not have electronegativity, right? They're not going to be pulling electrons closer. But I can split this up right here. Slightly positives this side, slightly negative by the oxygen side, slightly positive over here. And then we have our polarity moment of this dipole moment. NH3. All right, so we have nitrogen. I usually draw it like this. Hydrogen, 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 right? All right, so let's label these. Nitrogen is more electronegative than hydrogen by quite a bit. So let's label these as partially negative, partially positive, partially positive, partially positive. If you look here, you can draw a line that separates the atoms. Nitrogen side, partial negative. This is partial positive. This is polar. And if you want to draw the electronegative, or we should be drawing that, right? It's going to be the positive side here, pointing to the negative side. And that's the dipole moment for NH3 or ammonia. All right. Well, if you wanted to check out the polarity simulation, you can. So I'll show you how to get there. Oops. Let's copy and paste this, but you can just go to Google and you go PHET, and you can just put polarity, polarity. This one is a little funkier. I think it's an old one, but you can do two atoms, three atoms, or real molecules. I suggest real molecules. They're kind of easier to click through and figure out. So HF, you could draw the bond electronegatives. Oops, sorry. Let's see here. Bond dipoles, molecular dipoles. There's one where you could see I think you can see the deltas on here. Oh, here you go. Partial charges, right? Let's get rid of this. You can see the delta positive, delta negatives, right? You could pick different molecules, see what they are. You can click through these different options. But yeah, it's a good way to figure out kind of polarity. You can rotate the molecule so you can actually see kind of where the polarity is and what the molecule looks like in 3D. But yeah, check it out. And yeah, thank you very much, and I will catch you on the next video.